Now that we know how to name binary compounds, we're going to learn about polyatomic ions and naming compounds with polyatomic ions in them. Now, polyatomic ions are just ions that have two or more different elements. Although the individual atoms don't have a charge, the group as a whole has an overall charge. Multiples of a polyatomic ion are indicated by placing the entire polyatomic ion in parentheses, like in magnesium nitrate. Nitrate by itself has a 1 minus charge, and it looks like this. Now, if I need multiple nitrates, I have to put it in parentheses to indicate that I need more than one. It's like a little family inside the house. The parentheses are the house, and I have two of these little families inside the house. That's what that means. Because we needed two nitrates to balance the 2 plus from magnesium, because magnesium is in the second group on the periodic table. Here are some common polyatomic ions. They should be listed in the guided notes so that you have them for easy reference. You can use your notes on the quizzes, so take advantage of that. Use your notes to be able to write the names and identify them because you'll need to know them for your exam. But you can see here the common polyatomic ions: ammonium, nitrite, nitrate, sulfite, sulfate. You can see that there is a slight difference between like sulfite and sulfate, chlorite, chlorate, nitrite, and nitrate. If you look at that, you notice that you have a base. 8 is basically the base. And then ite is one less than what the base has, one less oxygen. So if the base has 4, the ite version has 3. Same charge, but different number of electrons. Same thing. 8 has 3, the ite has 2. Hypo has 2 less than the base, and per has 1 more than the base. So sulfate is a common one, nitrate is a common one, ammonium is common, carbonate, hydroxide, and phosphate. Those are the more common ones. Now, to name polyatomic ions, you're going to follow the same rule that you use in naming binary compounds. First, you name the positive ion, followed by the negative ion. Do not change the ending of the negative polyatomic ion, though. The name of that polyatomic ion stays the same. So, if I asked you what the formula for calcium carbonate is, we look at the periodic table and we see that calcium is in the second group. So it has a charge of 2 plus because it loses those 2 valence electrons. Carbonate, if we look on that chart, you'll see it has CO3 2 minus. So if we wanted to make a compound out of these 2 ions, the 2 plus and the 2 minus cancel each other out, so it would just be CaCO3. That would be the formula. What if I said, what's the formula for aluminum sulfate? Well, let's look. You can say aluminum, and I'm actually going to ask you to pause and try to answer these two, and then we'll answer them together so that you could check your answers and make sure that you got them correct so that you understand properly. Okay, aluminum sulfate. Aluminum, if you look on the periodic table, is in group 13. That means it has 3 valence electrons. So it's 3 plus. If you look at that chart that is in your guided notes, you'll see that sulfate is SO4 2 minus. Now, here we have to do our little crisscross and drop. Crisscross and drop. Now, it's easy for aluminum because you say, well, aluminum and that 2 becomes a subscript. But with SO4, you need 3 of those. If I did this, we don't need 43 oxygens. I need 3 of this whole group. Remember to put them in their little house. Put the group inside its little house. Keep it nice and cozy. We need 3 of them. So anytime you need multiples of polyatomic ions, they always go in the parentheses. Now we're going to go backwards. We have this compound. We need to name it. Well, if you look at the periodic table, Li is lithium, and PO4, if you look in your chart, is phosphate. So the answer is lithium phosphate. We do not change the ending of polyatomic ions. They always stay the same. If you changed the ending of phosphate to ide, you'd have phosphide, which would mean just the ionic version of phosphorus, which is way different than phosphate. So keep the polyatomic names the same regardless. Now, when you're making compounds of transition elements, remember I told you that you can't predict the charges. So it's a little different in terms of naming. So with transition elements, they're metals. They're going to still form positive ions. But most transition elements, with the exception of zinc, which always has a charge of +2, and silver, which always has a charge of +1, will usually form more than one type of iron or ion. Example, you have iron here, which is 2 plus, and 3 plus. You also have copper, which could be either 1 plus or 2 plus. Zinc and silver, as I told you before, are the exceptions. They only form one type of ion. Zinc is 2 plus, silver is 1 plus. So to name transition elements that are not zinc or silver, we use Roman numerals to indicate the ion's charge. Now the numeral is enclosed in parentheses and placed immediately after the metal name. This is called the Stokes system. So Fe2 plus is iron 2. Or if you want to use the Latin name, ferrous. Most people write it using the Stokes system with the Roman numerals because that's more automatic. But my mother's age, they used the Latin ferrous, ferric, cuprous, and cupric. And so I learned chemistry from my mother, who taught me the ferrous and ferric and cuprous and cupric. And I had to remember that iron made a 2 plus or 3 plus, copper made a 1 plus or 2 plus. And she taught me the high, I see Lois, meaning if it's the higher charge, it's going to end in ick. So the high charges ends in ick. So you could see here, Fe3 plus, that's a higher charge, it ends in ick. Copper 2 plus has a higher charge, it ends in ick. Low, if it has a lower charge, it ends in us. So copper 1 plus is a lower charge, us. 2 plus for iron, ferrous, it's the lower charge. So you can see. So if you ever run across the Latin names, you will know what it is. You'll be familiar with it. But typically we just use the stock system. It's more straightforward. Now, names of metals that commonly form only one cation do not include a Roman numeral. Silver doesn't, zinc doesn't, aluminum, magnesium. If it only makes one cation, you don't include the Roman numeral. Now, even if you use Roman numerals to indicate the metal form, you still name the positive ion first, and then you follow it with the negative ion. Here we have iron 2 chloride or ferrous chloride. It's still named positive ion first, followed by the negative. So I want you to pause, answer these, and then come back and we'll review them. So let's look. We're going to give these names. FeCl3. Well, looking at the periodic table, we know Fe is iron, and we know Cl is chlorine. But we also know that we change the ending to IDE. So this is iron chloride. We're missing something though. We need to know what iron it is. So let's look at this. We know that we have to figure out the charge. We know that we had Fe and Cl3. These, if we go backwards, we can know what it was. So that means we have Fe with a 3 plus, because it's a metal, it's going to be positive, and Cl minus. So what should go in the parentheses? The 3. So it'll be iron 3 chloride. All of these are transition elements, and all of them make more than one charge. So we have to state which charge it is whenever we're writing our names. So here we have Cr, which is chromium. We're going to have our parentheses here, and this is nitrate. Again, bring these up. This 3 would end up here, and chromium, we only have one chromium, so that's 1. So what charge is chromium in this compound? It's a 3. So this is chromium 3 nitrate. Okay, let's look here at copper and bromine. So we know this is copper. It's a transition metal. It makes more than one charge, bromine, but we can't leave it as bromine, we have to change the ending to "ide." We'll do the same thing. Take the subscript, make it the opposite superscript. So this becomes a 2. This is a 1. So this is copper 2 bromide. I'm going to give you some prefixes that are used. And this should just say number, not molecules of water. So I apologize. That's not correct. So if we look at this, we're going to have some prefixes for naming covalent compounds. If you have one of a type of element in a covalent compound, the prefix is mono. If you have 2 of that element, it's di. 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 hepta, 8 octa, like an octagon, 9 nona, and 10 deca, like a decade. So when we write binary inorganic compounds, we write the name of the first nonmetal, and we follow it by the name of the second nonmetal with its ending changed to IDE. So first write the element that's farther to the left in the periodic table. So if we look at the periodic table here, and if we had a compound made between nitrogen and oxygen, nitrogen's the farthest to the left. Right side by side, nitrogen's farthest to the left, so it's going to come first whenever we write a compound. That's what that means. If both the elements are in the same group, though, so in the same family vertically, you're going to name the first element that's closer to the bottom of the periodic table, like sulfur dioxide. Sulfur and oxygen are in the same group. So sulfur is closer to the bottom, so it's going to come first. Now, you'll add a prefix to the name to indicate the number of atoms of each element that are present. And you'll use the same prefixes that are used for hydrates, which are these. If the first element only has one atom, you omit mono. So here, like carbon monoxide, nitrogen monoxide. Mono never starts the name. So carbon monoxide, nitrogen monoxide, mono's only going to be the second, or the second element, if it only has one. The vowel combination is OO or AO, and they appear next to each other. You drop the first vowel. So nitrogen monoxide, instead of saying nitrogen monoxide, you drop that first vowel and it becomes nitrogen monoxide. So let's do a practice. I want you to try to answer these and then push play and come back and see if you were correct. So let's try to answer these. We have N here, which if we remember is nitrogen. We only have one, so we don't have a prefix. Here we have oxygen. How many oxygen do we have? We have one. So we say mono, and then oxygen becomes oxide. I don't put two O's together like that. It's not monooxide. We take one O out, and it's monoxide, like that. Okay, let's look at the next one. Okay, how many nitrogens do we have? We have one. So we just start with nitrogen. Then we have oxygen. But how many do we have? We have two. So it's nitrogen dioxide. And we're done. Okay, let's look at the next one. We have N2O. So we still have nitrogen, but how many do we have to start with? We have two. The prefix is di. So it's dinitrogen. How many oxygens? One. So it's monoxide. Our last one, we have two nitrogens. The prefix for two is di, dinitrogen. How many oxygens? Five. Look at your chart. What's the prefix for five? Like a pentagon. It's penta. And oxide. So we don't say pentaoxide. We don't leave it at that. So what do? You drop the first vowel. So it's pentoxide. Dinitrogen pentoxide. If you have questions, let me know. Okay, to write the formula of a molecular compound, you're going to write the symbol of each element in the order given in the name. Then you'll add the appropriate subscript after each element using the prefixes. The prefixes will tell you how many of each you have. Water is dihydrogen monoxide. HCl is hydrochloric acid. Not everything do you use the prefixes for. Sometimes you use the common names. H2SO4 is sulfuric acid. H3PO4 is phosphoric acid. HNO3 is nitric acid. This is acetic acid, which is in your vinegar. NaOH is sodium hydroxide. KOH is potassium hydroxide, and NH3 is ammonia. Ammonia is often used in a cleaner. You'll find phosphoric acid in your soft drinks that you drink. It's a strong acid, so that is why dentists will ask how much pop you drink if they notice that your enamel is coming off. Now, when naming organic compounds, make up the largest class of molecular compounds known because carbon is able to bond to other carbon atoms in rings and chains. And we're going to spend the last week talking about organic chemistry and how to name more organic compounds. But I'm going to just introduce it to you here. Hydrocarbons are organic compounds that contain only the elements hydrogen and carbon. And this is what you find in your fossil fuels. Your fossil fuels are your gasoline, your natural gas. your kerosene. Those are the things that give us fuel to power different things that we use on a regular basis. Now, the simplest hydrocarbon is methane, which is CH3, and the next is ethane. The names of hydrocarbons are derived from the number of carbon atoms in the molecule. Remember, molecular substances are substances that have atoms held together by covalent bonds. They will have variable properties. If you're ionic, we know it's going to be hard and brittle and conduct electricity. But it's different with molecular substances. They have properties on a whole spectrum. Butter, we know it's soft. We can melt it easily. Rubber is elastic. And diamonds are hard. You're not going to bounce a diamond and play ball with it. But rubber, you'll bounce the ball and play with it. Butter, it doesn't bounce. Now, usually, molecular substances have lower melting points. They're not as hard as ionic substances, and they're less soluble in water than ionic substances because they're not electrolytes. We can separate substances, though, in a mixture by evaporation of a liquid and the subsequent condensation of its vapor. We mentioned this our first week when we talked about distillation. Now, molecular substances have weak bonds and they're easily broken. And that weak bond explains the softness and low melting points. Molecules can vary in size. You can have one carbon, CH3, and that is the smallest hydrocarbon, or you can have chains of carbons, 20 carbons in a chain. So that changes the bond strength between the molecules as well. Now, if two or more atoms of the same element bond together, it's called a molecular element. This is like oxygen, O2. That's a molecular element. H2, I2, Br2. I call them the Hofbrinkels. That's how I remember them. All of these are molecular elements. They're not compounds, they're molecular elements. O2, H2, Br2, I2, they are never found singularly in nature. They are always bonded to something else, even if it's by themselves. It's like the person who can never be single. They always have to be dating someone. That's what these elements are. These are the 7 diatomic elements that are molecular elements. The Hofbrinkels, all except bromine and iodine, are gases at room temperature. Iodine's a solid, and bromine is a liquid. Now, molecules of a single element that differ in crystalline or molecular structure are called allotropes. Oxygen and ozone are examples of allotropes. Oxygen we need to breathe and live and survive. Ozone would kill us if we breathed that instead of oxygen. But ozone is extremely important in protecting us in the stratosphere from the harmful rays of the sun. The ozone was damaged whenever I was a child. We'll talk about that whenever we talk about organic chemistry as well. But luckily, it is repairing itself after we've made some changes to our manufacturing. Now, the properties of allotropes are different, even though they have the same element, and that's because their structures differ. We know ozone's toxic. It's also part of smog. So if ozone is around where we can breathe it, then it's damaging. But it has its purposes. In the stratosphere, it's protective. And we can also use ozone to purify water and remove odors because it oxidizes those smelly compounds into smaller compounds. So it's useful, but it's toxic if we're breathing it in. Phosphorus also has three common allotropes, and they actually have different colors. One's white, one's red, and one's black. And carbon has several allotropes. You have the diamond, graphite, which we write with, charcoal, which if you have a charcoal grill, you're familiar with, and fullerenes, which is what this picture is. Fullerenes have a potential to be used as superconductors, which would be awesome. So you can see how these properties vary vastly, even though they all are made of the same element. It's just the structure and how the electrons are shared creates its properties. It's pretty neat. Now let's look at formulas and names of molecular compounds. There are two types of molecular compounds. You have organic compounds that contain carbon and inorganic compounds which do not contain carbon. Both are covalently bound to each other. Remember that, it's important. But we're done for today, and if you have questions, always reach out.